All right, so what we want to do is just go down to the table before we attempt to solve this problem, the problem at the top. So there's a problem at the top that says that list the following functions from the highest to the lowest order of growth in terms of the size of the problem. So we're going to list these from the highest to the lowest order of growth. So that means the worst performing one is going to be the first one that we will put up. And then the last one will be the one that uses the least amount of resources. So if we were to plot the graphs, we would have, this one would have had the flattest curve in terms of its behavior. All right. So before we get to that, let's just look at this table here. So we have a set of classes of algorithms, and they range from a constant, 1. So 1 is a constant, 2, 3, 4, 5, any number that you can just count. A reasonable number would be a constant, right? So that means no matter how many, how large the input grows, it would not change because the resource that we're talking about here that is going to be used by the algorithm is constant, right? So short of the best case efficiencies, very few reasonable examples can be given, since an algorithm running time typically goes to infinity when its input size grows infinitely large. So we are saying that if you have a reasonable amount of input, then for a constant algorithm, it would be the best performing algorithm. However, if you were to have the input being an infinite number of input, then even though the resource that is used is constant, what would happen overall is that that algorithm would never finish doing its work because its input, it would always be getting input. Figure that? Constant in terms of resources. We are assuming that we have a finite amount of input. So n in this case would be a finite value, right? So let's say n would be 1,000 or even 10,000. It's a finite value. We can reach there. So therefore, if you have an algorithm that is behaving of this order of a constant behavior, it will be the best performing algorithm. Then the next one would be the log n. And log n here is log to the base 2 of n. So this algorithm, no, log n, I think that's one log, yeah, it's log to the base 2 of n, yeah, because linear here. So log n in this case is, so can I ignore this section that you're seeing here that says typically a result of cutting a problem size by a constant factor on each iteration of the algorithm. Note that a logarithmic algorithm cannot take into account all its input or even a fixed fraction of it. Any algorithm that does so will have at least linear running time. All right, let me say here, an algorithm that behaves in log n times, really what it's doing is that on successive iteration, it is dividing it by a term. So if let's say we say log n, and n here, log here would have been, we're talking about log to the base 2. What it would mean is that on each it will be dividing the problem by 2 each time. So the next iteration, the problem.
So, sir, that would be the case for like a binary search that
Right,
divides it by 2 every time.
right. So each time the problem size gets smaller and smaller and smaller. So each time you send the problem to the algorithm, the size of the problem gets smaller and smaller, and it does so of the order of the base of the logarithm. Right. So if it was log to base 3, what would happen is that each time, so if the problem size on the previous occurrence was 3 inches in length, by the time it has gone through that iteration, it would now be 1 inch. And the next time it would be 1/3 of an inch. So that's how the problem would be. So what you're noticing is that the size of the problem is diminishing until you finally get to a size that you cannot divide it anymore. You'll return the answer. So that's how the things like the merge sort work, things like the binary tree work, that kind of way. All right, so then we have the linear behavior. And these are algorithms that scan a list of size n. So if I ask you to count the members in your class, what you would do, you start counting from the front of the class to the back of the class, and you would have counted all of them. So that's a linear count. So you count everybody. So you examine them once and count them. Then the next one would be n log n. All right, so n log n is an algorithm that that would be going through the problem. If we were looking at a merge sort, or yeah, let's say we had a merge sort that we were doing. What we would have done on the first iteration, when we sweep across the list, what would we do? And can someone tell me what would you do the first sweep across the list? So I'm saying that the logarithmic behavior would be of and the linear arithmetic behavior would be of the order of n log n. So if we see a function that behave of this order, then it falls into this class of algorithm. An example of that would be like what we say, the divide and conquer algorithm, which would be the merge sort, the quick sort, as two of the well-known examples that we do. Then the next one is n squared. And this is a quadratic behavior, all right? So typically, this characterizes the efficiency of the algorithm and this algorithm would have 2 embedded loops. So for example, we'd have one loop, one outer, the outer loop would say for I equal 1 to n, and the inner loop would say for k equal 1 to m, where m and n are equal. What would happen in that case is that both of them are equivalent. So the worst case behavior would be n multiplied by n. And that would have given you a n squared behavior, and that would be quadratic. Then we have a worse, an algorithm that even behave worse than the quadratic, called the cubic. And this one would be order of n cube. Order of n cube. So these, when we look at things like matrices, where we have to where we do transformation of matrices, etc., typically we'll see those algorithms behaving like in terms of cubic, they have cubic behaviors. Then we have the algorithm that is 2 to the n. Okay. So n cube is cubic. And what we're saying here is that the behavior of an algorithm that is cubic, examples of those would be where we are working with a matrix. We are finding determinants, and we're doing transformation of matrices, etc. Then we have another algorithm, which would be an exponential algorithm in terms of its behavior. Note, although we are showing these behaviors, typically an algorithm that is behaving as an exponential, or even worse than that, as a factorial, are not algorithms that we would really desire to use, because those algorithms would never finish in our lifetime in terms of the runtime. They would take years to converge and to return the answer, right? So with this table, I want us to go through the table above and identify which of these functions are the worst and which are the best behaving. So let me, all right, so here are they. So we have 1, 2, 3, 4, 5. We have 15 of them. 15 of them. And we are asked to list them from the worst behavior to the best behavior. All right, so based on what we are seeing, so I wanted to use the table that we have here, this table, and use that to give me your answer.